Well, it's really a gratifying thing to see so many young, bright minds in this hall. And I'm sure you are excited to know more about nano in this next 1.5 hours. So like a few minutes back, can you say no to nano? No, because you want to learn about nano, right? So that's a tricky thing, no to nano. You can't say no to nano. So, so what we have been doing in this conference for the 9th year, we are now here for Bangalore, India Nano. And we always feel that nanoscience is a young subject, relatively young subject. It's an interdisciplinary subject. It cuts across the boundaries between different subjects in science, be it physics, chemistry, material science, biology, engineering. There is no barrier in this area, in nanoscience and nanotechnology. And there are many, many exciting things happening in this field over the last 20 years. So what we thought was, we'll bring to you three very well-renowned experts in this field who will talk to you on 3 different topics. And then there is much more beyond these 3 topics, of course, but this is just a beginning, and I'm sure you'll take up from here and develop your own interest. So first of all, let me say that Professor Rao could not be here due to some other pressing engagements. And I will be giving you about 5 minutes introduction, followed by more expert talks by Professor A.K. Ganguli, Professor Krishna Ganesh, and Professor P.S. Anil Kumar. So this is just a slide to remind you, it's a very, very famous talk which Richard Feynman gave. You know, he's the Nobel laureate in physics, in high energy physics, but in an evening talk in Caltech, he made a very profound statement. He gave a talk that it is on the web. You can type. There is plenty of room at the bottom. You will get his talk. And he said in 1959, much, much before nanoscience was even thought of, that the ability to manipulate matter at nanoscale, so nanoscale means roughly less than 100 nanometer, in order to change properties and functions which will result in new materials, devices, and systems. Now here, just to give you a feel, I am sure you all know, 1 nanometer is 10 to the power minus 9 meter. We are talking of length scale less than 50 to 100 nanometer. And for your just memory, your hair thickness is about 100 micron. And the blood cell is about 7 micron. So that's the length scale, and we are talking much, much smaller than that. So we will be looking at systems which are in this nano regime. So what are the key things which happen, which you will see in the next 3 presentations, 3 discussions? First, you will have, when you have such a small thing, then you have large number of atoms on the surface, which is a sizable fraction as compared to the bulk. Because if you take a bulk material, most of the atoms are inside and you have only few outside, the ratio. But in nanomaterial, the surface atoms are quite comparable to the atoms in the bulk. So with the result, you will immediately get huge activity of nanomaterials just by sheer surface to volume ratio. And this will come out in the properties like catalysis and high activity of nanomaterials and so on. Then you will get new functionality. So this is just a slide to show various length scales. Sorry, that if you have 100 micron, it's like optical microscopy you will use. If you are 1 micron, you will use electron microscopy. And if it is like 1 nanometer to 10 nanometer, you will use new tools called surface probe microscopies, which include atomic force microscope, and you can use scanning tunneling microscope. These are the new eyes and ears which you need to understand and even characterize these nanomaterials. So this is what I was saying, that a large surface area of this material makes them chemical and biological activity, catalysis, and then you can get novel phenomena when you go to nanomaterial. Again, it will be brought out in the two presentations which will be done by Professor P.S. Anil Kumar and Professor Ganguli, that how you can have novel phenomena and properties at nanoscale, which are not there in the bulk domain. So bulk, the reason is that the electrons, holes, phonons, they all get new issues when the size is confined, because they are not free to move around in the whole material. They are confined. So sheer confinement gives them quantum size effects, the effects which you get due to quantum mechanics. So nanomaterials are beautiful because you can see quantum mechanics at work at room temperature in these materials. So this is what will happen. And of course, if you make the devices small, electronic devices, they will consume less energy, they'll be much faster, and this is what will happen in nano devices. And this is where the Moore's law says that the chip power doubles every 18 months, and already you know in 2014, the length scale in the Pentium chip, Intel chip, which was there right from 2014, is 35 nanometer. So nanometer is in your daily life. So many electronic chips are already having the devices at this length scale, and this 35 has come down, and that needs different techniques to make it, and already it is occupying our life. So many nano things are in your life, like this quantum lasers with quantum dot lasers and so on, so which you use in your daily life in a CD reader and so on. So this is something which is making this field accelerate, because the devices are huge and the market is huge. So this is what you will also see in the next talk. You will also see in the literature, people will talk of two-dimensional materials like sheets, very thin sheets like graphene. You can also have one-dimensional nanomaterial like carbon nanotubes or the rods. And then you can also have zero-dimensional material like a quantum dot, like a nanoparticle of 1 or 2 nanometer. So in the literature, they are called quantum dots or zero-dimensional material. So you will see in the next three discussions how these are used for various applications. In nanoscience, needless to say, size matters, shape matters, and composition matters. So here you can see that if you take a semiconductor like cadmium sulfide or cadmium selenide, which has a typical emission in some wavelength, visible light, but moment you make them small, they will have all different colors, and you can see that from the same material, you can get blue emission, green, and yellow and red. Same material, but the size. If you vary the shape, again you can get similar effects. So this is where you are playing God. You are making whatever material you want in the laboratory and get the optical and electronic properties on your command. They have enormous applications, and one application, I don't know if Professor Ganesh will talk, that you can use them inside the cell. You can use imaging of the cell on the right side. These are the semiconducting nanoparticles as fluorescent tags in biological things. If you have metals, again you get very exciting properties. You know, you all love gold because of the shine. But now, if your gold is actually 50 nanometer, I'm sorry to say your necklace will be green. C is again gold, but nanoparticle. And this has come because what is called surface plasmons, the electronic properties of the gold, when you are at a nanoscale, it changes. So you can see that gold 50 nanometer is green, silver 90 nanometer looks with white, but 40 nanometer looks blue, extreme E. You can see, you can now play what color you want, and this was used in the glasses in this by the Romans and even earlier times in churches when they did this, the colored glasses and the images. So they were using the metal nanoparticles to color them. So this is something which we will, I'll stop here to say that periodic table, huge number of elements. I am stopped at 110, but this is, now it has gone to more. And now you can do many of these materials in the nano form. So the whole world is opening for you with new properties. Many of them have not been named into nano. Most of them are studied in the bulk form. Their applications are in bulk form. But imagine when most of these materials and their combinations can come to you in nano form. So your generation really will explore many, many more new things in nanoscience and nanotechnology. The imagination is the only point where you have to work on. You have to make your imagination work. So that's the only limitation. The limitation is what you can think in terms of these elements, in terms of the compounds, in terms of various combinations, new combinations. And this is where the field is extremely exciting. Though it is 25-year-old field, it started in 1990 with one declaration by US, but it has gone a long way, and now still it is very, very fresh. So the advantage of this field is that it is still opening many, many doors almost every day. And what it tells you is that when you are ready to make contribution in this, it's all there. And this seminar, this meeting of only 85 minutes is only to whet some of your appetite. We will not be covering everything. We'll be covering a part of it, but just to make you think what all you can do. So I'll stop here, and I will now have invite them to have 3 presentations, one by one. And what we will do is, after about an hour, I have requested them to limit their presentation to 20-25 minutes, and hopefully we will be left with time. So please note down your questions and your name and college or school, and put it on a slip. So we will have volunteers collecting those slips, and then, because many of the questions we have found in the past are common, so it's not just a good repetition. We will select some questions, and our experts will answer them. And we will have a very interactive discussion at the end of the session. So this is the agenda for the day, and we will start with the first talk by Professor Ashok Ganguli, who is the director of an institute of nanoscience and technology in Mohali, which is near Chandigarh. And this is a new institute, and he is the first founding director, and he will tell you what nanoscience is and what are the exciting things happening around us in this field. So we will stop, I'll stop here and invite Ashok to give his presentation. Ashok.
Loaded, huh? My talk is not yet 12. So I'm going to give you a little brief introduction to nano and then give you examples. First, I must tell you, nano is a very small part of science, and science is exciting. That's why we are here. We are celebrating. We are all working in science for 40 years, some of them maybe more. So point is, nano is part of science, and the beauty of thing is science comes by looking at things around you. So if you care for science, that means you look at living things or exciting things happening, how satellites work, how the International Space Station is working. It's all science, right? Nano is also part of science. So the first quality for all of you should be observation. This is what I want to tell you. And the first observation, just by looking at the blue sky, Rayleigh explained, got a Nobel Prize in 1919. No equipment, just the brain, okay? Why I'm telling you this, I'm sure all of you know why blue color comes and why red color during sunset. The scattering of light explained by Rayleigh. But C.V. Raman also explained scattering, a different kind of scattering. Very difficult to find by ordinary detectors, but he found it due to great brain of his. And I'll come back to C.V. Raman at the end. That's why I want to show you this slide. All of you should know the date, February 28, 1928, when he discovered this in Indian Association of Cultivation of Science in Calcutta, which today is a government institution, was run privately with his own money. He used to work in the evenings. This is Raman, did many things which you don't know probably, and you should read his background and the difference between Rayleigh scattered and Raman scattered, which he observed. See, all of you who are interested in science and the excitement, you should go back and see the profound understanding he had to put the green filter to observe the Raman effect, okay? But let me come to another great, probably the world's greatest scientist, Michael Faraday. Because he found so many things in your chemistry books. All of you talk of electrode, anode, laws of electrolysis. Everything by Faraday. Went to school only for 3 years. He made the first motor transformer generator in the year 1821-30, okay? Why I'm telling Michael Faraday? Not only because he's the greatest scientist, because he's the first man to make nanoparticles. And that's the nanoparticles he made on the top right-hand corner. That's Faraday's gold nanoparticles made in 1857, which is kept in Royal Institution in London. You can go and see it. And so Professor Sood was mentioning about gold nanoparticles in glasses. 4th century AD, people knew how to make these colored glasses using metal nanoparticles. But they did not know that these are nanoparticles at that time. But these are gold nanoparticles. But you can have other metal nanoparticles embedded. So the story of nanoparticles is very old. In our old traditional medicine, we put sometimes, these bhasmas. What are these? These are nanoparticles. Now Government of India has big projects. Jamia Hamdard has big projects on understanding what these nanoparticles are doing in our traditional medicine, which is Unani and Ayurveda, okay? So gold, following on gold nanoparticles are great catalysts. The big particle of gold does not oxidize carbon monoxide to carbon dioxide. But the small particles, the nanoparticle oxidizes. Great property, you don't want carbon monoxide. It's a poisonous gas, right? You want to convert it. Gold changes colors. Gold changes from a metal to an insulator when you go from large size particles to small size particles, okay? This is coming 2016. I have traveled very fast. You can make gold foams. You see, that's a peacock feather. On top, you have this gold aerogel. Most of it, 80%, there's nothing. Okay, 2%, not 80%, only 2% material is there, right? So this is 20-carat gold foam, and this was made in 2016. It is floating on coffee. This is another new finding on gold. You can use gold to do what is called optical distillation. What is this optical distillation? We all do thermal. We heat solvents and take out the high boiling solvent first in a mixture of solvents, okay? That is traditional. That is known for 150 years. This is new. You are using light in the presence of gold nanoparticles. Heating those particles heats the top layer. And that's a better thing to do because you want the top layer to evaporate. This is called optical distillation. 2016. You see how every day new things are found in the world. This is using gold nanoparticles, okay? By the way, all around you have minerals, materials. The chair you are sitting, the fan, the air conditioner, everything has particles. But we can't see them because our eyes can see only to a limit of 0.03 millimeters. That too if you have perfect eyes, okay? So what happens to things below that? We need to use microscope. So this is using a scanning electron microscope. We are looking at micron-sized particles. Then if you go to atomic size, this is from your textbook. This is drawn from your textbook. So these atoms, can we see them? They are smaller than nanometer. Nanometer has already been defined at 10 to the power minus 9 meter. Atom is angstrom. Hydrogen atom is 1.058 angstrom. That's the diameter of hydrogen atom. The first picture of the atom, 1951, using field ion microscope. by Erwin Mueller, right? So remember this, the first picture of the atom, because sometimes people say people have not seen atom. They just draw in the notebook. Have you anybody seen? Yes, long back. Modern microscope, you can see inside the atom. This is a Titan microscope. It's called the aberration-corrected microscope. You can go inside an atom and go to resolutions, unbelievable, 0.05 nanometer. 100th of a nanometer is the resolution. It costs 35 to 40 crores, depending on the attachments. India also has around 10 or 12 such microscopes. I think 2 are there in Bangalore, okay? So these, you can go and look inside the atom. That's the resolution. This is the length scale. Nano is there, but you can go to smaller size. You can go to picometer. You can go to femtometer. Today, the world works on atometer. There are 2 labs in the world in United States, in Colorado. They work on atometer. Can you believe it? So small. What is a femtometer? Can anybody tell or think? Do you know anything in your school book which is close to a femtometer? Anybody, raise your hand. All of you have studied. That's the size of the nucleus. I'm talking about atometer, 1,000 the size of the nucleus. That means scientists have a way to do experiments with them. How do you do experiments? Because you can't touch them. You need probes to move them around. So scientists have developed those probes, okay? That means we can go even smaller than nano. So lots of unique properties are there in nano. This I won't tell you, electrical properties, magnetic properties, everything changes, okay? In biology, things change. You know, this RNA motor, it's in your body. There are so many devices made of carbohydrates, proteins, etc., which are natural, which are in our body. They are like machines. This is nanotechnology, living nanotechnology, and nanotechnology made by us, like some scientists made a layer of silicon atoms and put a DNA in between them and studied charge transport. So that's nanotechnology. Can you work in these dimensions, 40, 150 nanometers, and make devices, okay? This 1990 motherboard of a computer, right? You look at the chip, right? There's a silicon chip. Those pins you see actually are how many contacts you can make, how many circuits you can make. So in that dimension, which is probably around an inch, you have around 40 pins. Today, you may have 400 pins. The size, Professor Sood was mentioning that you have 35 nanometer dimensions. You can put so many pins. And that's the power of electronics today. The chip has got much more circuits which it can handle within that 1 inch size, okay? Your hard disk has changed. Now we have disks. You look at this 700 MB CD, which you used maybe 10 years back. Nowadays, nobody uses these disks. Today, the same disk, instead of that, I can buy a 25 GB Blu-ray disk. What is the difference? The difference is the laser which you are using to read, okay? So you are optically reading. That laser is using a wavelength which is very small, which we could not use earlier. We could not use a blue laser. Today we are using a blue laser. So blue laser has a small wavelength. Smaller the wavelength, smaller is the size where it can read, write, okay? So you are using very small dimensions. How this wafer is made, etc., I won't go, but this is how a component wafer is made, right from the sand, from silicon. So nanotechnology from the earth. You start from silicon, right? And you can make these disks, you make these channels, all these interconnects. These are the circuits. So today's nanotechnology, the one I have drawn, that scale you see is 5 micron, 10 micron. Today we are talking in nanometer. 35 nanometer was the dimension mentioned just now. And all this is done in clean rooms like this, which are called clean room. Doesn't mean that you clean with a broom. But clean room means every particle there is known. How many particles are there in the air? Which wavelength of light is there? Everything is controlled. It's expensive. A small room may take you few crores to make. But in these kind of rooms, you have to design these kind of circuits, okay? You can write with atoms. IBM wrote with atoms in 1989. There's a paper in Nature. Don Eigler is the scientist who wrote with atoms. It's a plate, nickel plate, where you extract nickel atoms and put xenon atoms. This has to be done ultra low temperatures, ultra high vacuum. Then only you can make atoms sit. Even people like you who are 60, 70 kilograms cannot sit quietly, right? We cannot be able to move. Atoms have no weight, very, very small. So they will move. How do you keep them quiet? Remove all their energy. That means lower the temperature. That's why you have to do. So you need to do that. It has been shown, technology. But the first atomic hard disk has been made after how many years? It was released last year, 2016. The way to write with atoms was known in 1989. The hard disk, atomic hard disk, was released in 2016. It takes that kind of time to make a technology from the lab go to the market, okay? And it uses chlorine atoms. So you know what are 0 and 1, binary. So the chlorine atom is there or not there. That's how they write in an atomic hard disk. Tremendous memory. It's expensive, not so common, okay? You can write with molecules. The next one is molecules. It is cheaper. This is very expensive. It's cheaper. But you can do it. This is E-beam writer. This machine costs around 5 to 6 crores. You write with ions. You can write with electrons. Okay, E-beam writer means you are writing with electrons, and you are making circuits. So why do you want to make such circuits with atoms or molecules? Why not with your pen? What is the diameter of your pen? The diameter of your pen is some half a millimeter, maybe, or 0.02 millimeter, right? But the diameter of an atom is around 2 angstrom, 0.2 nanometer. Make a ratio of that, 0.2 nanometer divided by 0.2 millimeter. How many orders of magnitude difference? Around 6 orders of magnitude difference. So if you have a book in which you are writing with your pen, and I write with my atoms, I can have 1 billion books within your book. So all the books of maybe your school and all the neighboring schools come within one book. That's the power of going smaller and smaller. We're having everything in small size, okay? Today, I don't think this will work. Yeah, it's not. Oh, it's working. You can see one molecule at a time, okay? This is called single molecule spectroscopy. You use laser beam, focus it on a volume which is femtoliter in size. So you can not only write with atoms, you can observe one molecule. When you go to a doctor and give blood for malaria testing, you give some drop of blood. You know how many molecules are there in a drop of blood? Anybody idea? 100,000. Any idea when you give a drop of blood, how many molecules are there? Anybody? Give me the order. If you come within, nobody? You have to go basic chemistry, huh? Trillions? 10 to the power how many? In one drop of blood, you have around 10 to the power 20 molecules. Avogadro number is what? 10 to the power 23, right? One drop of blood, maybe say 0.05 ml. Okay, 22.4 liters has 6 into 10 to the power 23 molecules. So how much will 0.1 ml have? 10 to the power around 20 molecules. So all your doctors or all tests are done on 10 to the power 20 molecules. You have no idea how individual molecules are. Maybe half of the molecules are fine. That means half of the molecules, blood, are not, cells are not affected by malaria. But today we can do each individual molecule by looking at these kind of things. Modern technology, convert energy. You are chewing gum, convert that energy using a nano generator, a piezoelectric material which is attached to your jaw. It converts your chewing motion into electricity. Okay? This is modern technology. This is terahertz technology. Terahertz is a very new phenomena. You must not have heard because you have to generate terahertz in the lab. And using terahertz technology, these rays can penetrate and can show you that this guy is carrying a knife in his newspaper. That's the power today. So airports or security services can utilize this technology without screening you. They can see from a distance what are you carrying. Okay? And where is terahertz? If you don't know, between microwaves and infrared, that is terahertz. Okay? And this kind of machines are used. Sometimes in airports you will see that. Now let me come to nanostructures in nature. This hornet has got nanostructures in its body. It generates electricity from solar energy, what we all want to do in the lab, right? and it also air conditions. It is also has thermovoltaic properties. Still, everything is not understood how it works. But many things are understood. You can read. There are papers published in 2000, 2001, where they have tried to understand all the properties of this organism. If you keep this organism, put two electrodes and connect to an ammeter or a voltmeter, you will see that in the night, you will see a current. That means it is working like a battery. In the daytime, it will not give out any current because it is absorbing photons. It is not generating any power. So you can do this measurement in the lab, and you will see that only when the light is off, there is a sudden surge in the current. That means it is giving out electricity, like the battery. So this is nature's way. Nature has made this battery using solar radiation. It is converting into electrical radiation. Okay? There are so many objects which walk on water. You know that? You have seen ants and all walking on water. We can't walk on water. Why is that? There's nanotechnology under its feet. If you take a cross-section of its feet and look under the microscope, you will see these microhairs. Within each microhair, there are nanogrooves. And what happens? Air gets trapped in these nanogrooves. And this air, under its hairs, under its leg, makes it walk on water. We can't do it because we don't have these kind of nanohairs under our leg. Similarly, you use Post-it pads. What are Post-it pads? They have got fine nanostructures under its body. These are called adhesives, self-adhesives. You can use it and reuse it. The technology made by 3M Corporation in the United States and patented it is because they understood how these kind of organisms walk and looked at under their feet. And this is a great subject today where chemical engineers work on this, on viscoelastic properties and adhesion. Okay. You must have looked at butterflies with different color. Now this butterfly, you can see sometimes brown, sometimes blue. And this is because it has got nanostructures on its wings. And these nanostructures are sometimes small, sometimes large, depending on whether it's flying or whether it is on the bark. When it has got small structure, which I can see using a microscope on the left side, underneath, that's a microscopic picture of its wing, you see small holes. On the right side are large holes. So when the visible light is falling, it scatters and gives out blue color when the small holes are there. Okay? The blue is a shorter wavelength. Okay? On the other side, you get the longer wavelength. That gives the brown color. And this subject today is called nanophotonics, where you take, say, a polymer and make holes of different size. Use the same color of radiation, and you can get different colors depending on the order, arrangement of the holes, and the diameter of the holes. So whole subject of nanophotonics, based on nature is already having that. Okay? Nature has tremendous structures like the beak of this bird. This is a South American bird called the toucan, one of the hardest materials naturally occurring. If you take a cross-section of this, look under the microscope, you will see it's a layered structures, all proteins. This is keratin, which is there in your hair. It's there in your nails. But inside, you see a lot of porous structure. This kind of network is light and strong. And this has been used by engineers, materials engineers, on the aircraft wings of a US fighter plane. Okay? We learn from lizards that they can climb. How do they climb? Again, nanotechnology under its leg. You have these are called hierarchical structures. So this whole subject of hierarchical science, which is very popular in physics and chemical engineering, gives us this power of adhesion. And this is what is a great subject, and scientists have made this. These are artificially made in the lab. You may recognize one of the names, Anil, who got the Nobel Prize for graphene, and that is his paper of making a polyimide gecko tape. What is gecko? In the United States, a lizard is called a gecko. So it's called a gecko tape because the tape works like the feet of the lizard. Okay? You know, lotus leaves, this is the most simplest example that we all tell school children, that the lotus leaf has super hydrophobic properties because it has nanostructures. If you look under the microscope, you will see these nanostructures which make the surface properties such that the spheres are formed. And using that, we make smart glasses like that, so that water rolls down the surface, take the dust particles along with it. You can make shirts like this where water droplets form. They dry fast. This is used for army people. Even in India it is made. The sharks have beautiful skin, but the whales don't have beautiful skin. What's the difference? The shark has nanostructures on its body. These structures do not allow bacteria and fungus to form. So scientists opened a company in which they make polymers. In the polymers, they make designs like nanostructures, and these can be used under submarines and in ships. And this person is in Northwestern University. He grew up in Florida, and I had a chance to meet him. And this polymer, he gave me how he made it. It's a very simple technique, but it does work beautifully. You see on the left-hand panel, very few bacterial cells. On the right-hand side, lot of bacterial cells after they kept it for some time. Penguins can live at -40. How? We will freeze to death. Ice will form. They looked at the feathers and found penguin feathers will never form ice because of the structure and because of an oily secretion from one of the glands. And so then scientists are now working on this to make coats which work like penguin feathers. They use this similar kind of liquid to spray on aircrafts so that ice doesn't form on aircrafts in the North Pole or in wherever you have. Otherwise, the aircraft becomes very heavy and cannot fly. So I have another 1 minute. You see photosynthesis. This is the membrane in photosynthesis, how plants make energy. This is a machine. This is a machine. I have a movie, but I don't have time to show how the plant machinery is moving electrons, protons, making ATP, making NADPH, and from that making glucose in two machines, the Calvin cycle, the light cycle, and the dark cycle. This is like a machine. Okay? This is a ribosome, another machine, making proteins. Professor Ganesh will talk about this. And this is about DNA helix and how the DNA replicates. So I'm going to stop. These machines are being made by man. The Nobel Prize 2016 was given to these three people for making nano machines. And this is a nano machine which works like a car, and this is their nano car. And the world's first nano car race took place in France in 2017. 7 teams participated. Okay? So with that, this is my last slide. This is where I come back to Raman. This is called the nano nose made by Israel, where surface-enhanced Raman spectroscopy is used, and Raman spectra gets enhanced. So even one molecule you can catch, so it can detect explosives, etc. So if you want to know about that, that's the thing. So I want to stop here and say thank you very much.
Thank you, Professor Ganguli, for this very fascinating tour of nanoscience and nanotechnology in different areas. I'm sure you would have noted your doubts, whatever it is, on a piece of paper. We'll take it at the end of the session. So now I'll request Professor P.S. Anil Kumar from Indian Institute of Science, Bangalore, to tell us in particular about these magnetic systems and where the nanoscience is at play in your daily life. Professor Anil Kumar.
Thank you, Professor Sood, for the introduction. So we will shift gears, and we will talk about a different topic, which is spintronics. So how many of you are using, can we have the lights, please? Yeah. So how many of you are using spintronics here? So today we will see how you are using spintronics and where you are using spintronics. Okay, this is just to give you an idea. We are in Bangalore, so Indian Institute of Science. You are all welcome for the open day of Indian Institute of Science. Is going to be in the first week of March, where you can see many of the labs at the Indian Institute of Science. So my lecture is going to be based on magnetism. All of you use magnets in your daily life. And I just wanted to tell you that this tiny electron which you have has got a magnetic property. You can consider this electron as a tiniest magnet which has got a magnetism with the spin up or spin down. You can say with the North Pole up or a North Pole down. So the electron has got two spins, up spin and the down spin. The spin of this electron plus the motion of this electron gives you the total magnetic property of a material. So we will be making use of this concept to discuss further what I'm going to talk about today. So what is spintronics? Spintronics means spin-based electronics. You all know that if you have an electron, this electron has got a charge as well as a spin, right? And you are all familiar with conventional electronics. In electronics, you start making use of, you use only the charge of the electron. You don't worry about anything else. When you talk about a diode or a transistor, you only worry about the charge of the electron. But nowadays, we started worrying about the spin of the electron along with the charge. That's why we have this new topic, which is called spin-based electronics, or in a short form, it is spintronics. So how are we going to use spintronics? So this is a view graph which is made in 2003. So here, if you look at, all these people contribute to the spintronics material technology. You need electrical engineers, you need mechanical engineers, you need physicists, you need chemists, you need material scientists. All these people contribute to the spintronics material technology, and what is coming out is amazing. You have magnetic field sensors, speed sensors, location sensor, angle sensor. So suppose if I have a magnetic field sensor, right? So it has got enormous applications. The spintronics gives you the best magnetic field sensor. So what is a good magnetic field sensor? If I have a magnet and a magnetic field sensor, how far I can go away from this magnetic, the magnet, and still the sensor senses this magnetic field? Or how small I can make this magnet, still this magnetic field sensor senses from a distance. So spintronics allows you to make tiny magnetic field sensors that can sense magnetic field at large distances. So what is the advantage of this? Imagine that you are bicycling every day, right? You attach a tiny magnet onto the rim of your bicycle and a tiny magnetic field on the fork of your bicycle, and when you bicycle, each time it takes one rotation, this magnet comes close to the magnetic sensor and it gives a signal. The next rotation, again it gives a signal. The total distance traveled, 2 pi r. The time taken, delta t. 2 pi r by delta t is the speed of your bicycle. For every rotation, you get the speed of your bicycle, right? And imagine that I want to open that door with a motor. So I connect a motor, I switch on the motor rotates, the door opens, but it comes and bangs onto the wall if you don't stop in time. Now imagine that if I have a tiny magnetic field sensor on the wall and a magnet on the door comes close to the magnet, it gives a signal is given back to the motor, stop. This stops. So it won't bang on the wall. So it has become a position sensor. Now it's your imagination only stops you where you can use this magnetic field sensor. If you take a modern car, you have as many as 35, 40 magnetic field sensors for different purposes. The one which I'm going to talk about today is the second one, which is the data storage. That's why I asked you the question, how many of you are using a computer? And the next one is magnetic random access memory, that if time permits, I will go through that. And the top column, we have not even touched there. So that is for the future. That's for you people when you grow up. Spin field effect transistor, spin memory, quantum computing, all these things are part of this. So let us see now what we are using and then move further. See, now if I consider a magnet, you are all familiar with magnetic hysteresis loop from your 12th standard textbook. Now I go one step ahead, and I say that I have a special magnet now. It is a single crystal magnet. What you are familiar with is a polycrystalline material, an assembly of magnets together. That's why you get a hysteresis loop which is curved. Now if I take a single crystal magnet, and I apply a magnetic field in this direction, I call this as an easy axis of magnetization. And if I apply the field in this direction, and if I reduce this magnetic field, and I get a hysteresis loop, which is resembling this. This hysteresis loop tells me that if I apply a magnetic field, it is magnetized like that. If I reverse the magnetic field at a particular field, which you all know is a coercive field, the magnetization reverses, right? I get a square hysteresis loop. This concept I'm going to use for the memory applications, right? Now in such a magnet, suppose imagine that this is a magnet, right? And I keep this magnet with this pointed edge towards you. When I keep it towards you, I call it as a 0 state. When this is pointed towards me, I call it as a 1 state. Now imagine I have two magnets, right? I take two magnets. If I keep both the magnets like this, if you read from here to here, what is the state? 0, 0. What is this? What is this? And if I take the, okay, we don't go for the third magnet. Now, with these two magnets, now I have created 2 bits of memory, right? This is precisely how you store information in your hard disk. 1 magnet, 1 bit. 2 magnets, 2 bit. And what is the state? 0. And this one? And this one? So you have 2 bits. Now, how many bits are there in your computer? Imagine that you have a 500 GB hard disk. So 500 into 8 into 10 power 9 such magnets. So if I take these magnets, and you know what happens if I bring 2 magnets close to each other? What happens quickly? Okay, make your life simple. If I bring 2 magnets like this, repel. If I bring these 2 magnets, attract. If I bring it like that, you must have done this experiment in the school, it goes like that, right? So now I cannot bring 2 magnets close to each other because if I write information in 1 bit, the other bit gets affected. So I need to keep them far away, at far away distance. Now I have to keep them at this distance. In this hall, maybe I can have maybe 5,000 such magnets, right? So in this hall, if I'm given with magnets of this size, I will make a hard disk whose memory is 5,000 bits, right? Now if I wanted to have 10 power 9 such magnets into 500, right, into 8, that means even entire Karnataka state won't be sufficient for me to keep my hard disk. So what is the trick? The trick is to make them smaller and smaller and smaller and pack them in larger and larger density. So if you look at here, I will have these individual magnets depending upon which is the direction of your north pole and the south pole. I write information like zeros and ones. And if you have, suppose, why did I say 8 magnets together? That gives you 1 byte. And suppose if you wanted to write the letter A, for example. So letter A means 0, 1, 0, 0, 0, 0, 1. So 8 magnets are arranged with this north pole towards you or towards me in this particular configuration, then I have the alphabet A. Similarly, if I have 0, 1, 0, 0, 0, 1, 0, alphabet B. So like that, we convert this information. This is how you store information in your hard disk. And for capital letter A and the small letter A, different characters are there. So that means everything can be distinguished with this set of 8 magnets. That's why you say 1 byte. 8 bits is 1 byte, because with this set of 8 bits, 8 magnets, you define everything. That's how you store the information in your hard disk. Now, as I told you, you need the entire Karnataka state to have a 500 GB hard disk with this kind of magnets. So what is the trick? The trick is to make them smaller and smaller and smaller. And if you look at something called magnetic force microscopy, you don't have to worry about it. That individual blocks tells me that the magnet which is sitting in your hard disk. So this is the hard disk of 2000. There is a reason why I kept that. If you take that hard disk, the width of this magnet is 45 nanometers. And the length of this magnet is 380 nanometers. So how small is 45 nanometer? How small is 45 nanometer? What is the diameter of your hair? Professor Sood said in the first lecture, 100 micrometers. Take your hair, vertically split 2000 times, take 1 piece out of it. Not along the length, that anybody can cut. So take your hair, vertically split 2000 times, take 1 piece out of it. That was the size of the magnet in your computer hard disk in 2000. And if you look at the evolution of the magnetic hard drive, you see this is the size of the bit as a function of time, and the size was 10 micron, 20 micron. Take your hair, vertically split 5 times, 6 times. That was the size of the bit. And as time progressed, the size has become smaller and smaller. And in 1998, suddenly the size started becoming much smaller. That's why if you take a hard disk of 2000, you see it is 45 nanometer. So what is the trick? What is the change that has happened at that point of time? that point of time, we started introducing spintronic devices in your computer hard disk, right? So what is the state towards you? 0. How do you know it is a 0? Because there's a pointer here. So in the computer, you cannot go and check whether this north pole is like that or like this. So there should be a mechanism of finding out what is the direction of this magnetization. So if I have a magnetic bit, you will have magnetic lines of force outside. Now I can bring a compass to find out what is the direction. A compass will tell you what is the direction of the magnet. But now the problem is that when you have 10 power 9 such magnets in small area, if I bring a compass, the compass will see all the magnets together. So he won't know what to do. Now the trick is, make the compass even smaller than the bit. So that if I have magnets like this, I bring a compass, and I bring on top of this magnet will tell me, yeah, it is towards you, it's a 0 direction. You bring it here, it tells, oh, again, it's a 0 direction. So this, making of this device, which is smaller than the size of the magnet size was only 45 nanometer, was a challenge. So we had the technology to make this magnet smaller and smaller and smaller. But we didn't have the technology to read this magnet from such a small area. That is why the introduction of spintronics in 1998 revolutionized your computer hard disk. Otherwise, without that, you may be sitting with maybe 100 MB or 1000 MB hard disk today, right? Now you have terabits of space. Now the second question is that, how do I go from here to here? I picked up the magnet and put it like this. So 0 state to 1 state. You cannot go to your computer and pick up each magnet and put it in the opposite direction. So you need to have a method of changing the direction at your will. So I showed you a hysteresis loop. That hysteresis loop tells you, if I apply a magnetic field in the opposite direction, which is higher than the coercivity, this switches. Now I cannot put a magnetic field to 10 power 9 such bits, because everybody will switch. So you lose the information. So now the trick is that you locally apply magnetic field. So you need to have another technology where you can locally apply a magnetic field of a width of 45 nanometer to switch the magnetization. So this is the right head that is in your computer that is working. So if I go further, if you look at your computer hard disk, you will have a yoke which is sitting here, so in which there is a wire wound around that creates a local magnetic field. So that local magnetic field switches the magnetization from one direction to the other direction, or make it 0 or 1 state. Adjacent to that, I have a reed head. This reed head is made up of giant magnetoresistive material. See, the magnetoresistance means the resistance of a material changes when you apply a magnetic field. Now, if I have my compass, whose resistance changes when it is exposed to a magnetic field, just by looking at the resistance change, I can tell you whether it's a 0 state or a 1 state. So, but the sensitivity of that sensors were very weak. That's why until 1998, we were going very slow. But in 1998, something got discovered called giant magnetoresistance that changed the way things looked at. The name itself suggests giant magnetoresistance. The resistance changes with a very large swing, so that even tiny magnetic fields you can pick up. That means even if I make my bit smaller and smaller, still I am able to get the direction. So that's how it happened. So now, moving forward, if you look at the growth of the areal density, you see that it was expanding or going up much faster. Now you see 2015 to 2020, nothing is happening. You had a 1 TB computer a few years back, now also you have. So that means, is it the end of the era, right? That means we will not have a better computer for future. So that question we will answer in next 2 minutes. And before that, let me just tell you, the first computer in 1956 made by IBM was sitting in a big hall like this. Because it's a big system, and it had 24-inch hard disks, 50 of them. Each hard disk needed to be cooled and separated. So all this electronics together, it was occupying a big hall like this. And the capacity of that hard disk was 5 MB. 24-inch disks, 50 of them, with the 5 MB and the density 2 kilobit per square inch. Now with this advent of nanotechnology and the spintronics, we could make the size of your hard disk on a 2.5-inch disk where you can hold 500 GB of information. You remember this magnet has now shrunk further to 15, 20 nanometer size, and that has made now our computers with terabits per square inch. Now, is the end of the day? The problem is, if I take a magnet, and if I start making smaller and smaller and smaller, here comes the nanotechnology in the opposite way. You lose ferromagnetism of a material when you make it in the nanoscale. So you don't want nanomaterials because I lose ferromagnetism. So you call something called superparamagnetism. So people said, okay, now we have reached the superparamagnetic limit. Now we have to think about alternative. What is that alternative? People started thinking about, if you come to Bangalore, you see high-rise buildings. If you go to a village, a palatial, property in which you have a small house. So people thought that, okay, we have to go vertical. So that means now this hard disk with the magnetization perpendicular, and the next generation with the perpendicular patterned media will have the dimension of this magnet of the order of 4 nanometers. So 4 nanometers means take your hair, now vertically split 20,000 times, and that is going to be this magnetic bit in your computer hard drive in the next generation. Hopefully in the next few years, again you will start seeing an explosion. The problem is that you can make now magnets which are smaller than 4 nanometer. But now you need to have a sensor that picks up information from smaller than 4 nanometer. That is a current challenge that people are working on. With this, let me just stop this talk. Thank you.
Thank you, Professor Anil Kumar, for this fascinating journeys for over the last 40, 50 years, how these devices have become really miniaturized. Thank you very much. Now we will go to the last presentation of this morning session, and then we will take question answers. May I request Professor Krishna Ganesh. He was director of Indian Institute of Science Education Research, Pune for 10 years, and now he has taken over the leadership in the new ICER at Tirupati. So may I now request Professor Krishna Ganesh to tell us nanoscience in medicine and biology. Krishna.
Okay, thank you very much. So, till now you heard about the external aspects of nano. Now let us see what happens if it enters inside your body. If these nanoparticles go inside, what are the kind of things that we can do? So, this is about nanotechnology in healthcare. Now, the whole biology, I think you heard in the first lecture about this beautiful nature, the whole biology operates in nano dimensions. The proteins, nucleic acids, the whole cellular machinery works in nanoscale. This just gives you some idea about the size. So what we are interested in, the nanometers 10 to 10 raised to the power of 2, that nanometer region, we are interested in this. Now, the DNA is about 2 nanometer wide, and hemoglobin is about 5.5 nanometer. This is just for the sake of a pin, is the size of the pin. These are magnified ones to show that. So nanoscale devices are about 100 to 100 times smaller than human cells. Just now you heard about the magnets, which are 1/200th or 400th part of a hair. So let us look at nanotechnology in medicine. I'm going to give you 3 examples. One is about how to detect diseases, diagnosis using nano devices. The second thing is, can we make, you heard the wonderful properties of the nanomaterials, the biomaterials. If they're, what are the kind of special properties they have and how we can use them. And the third one, which is a very important one, is about medicines. The drugs means medicines. It's not the drug, what you normally think of. So the nanomedicine, the tablets, what you take to cure diseases, etc., how the nanotechnology can help that. Let me quickly go to the next slide. So what are the things? So the nanomaterials you heard. One is nanoparticles, they shed water, they're hydrophobic. You had the example of lotus petals, right? So they can be functionalized also. You can take a nanoparticle and add something, chemically. So that is important in the case of drug delivery, that application. The second thing is silver nanoparticles are antibacterial. They can kill bacteria. The silver nanoparticles, not the silver thing, silver nanoparticles. I think all of you know about this Kaju Barfi. They put a thin layer of silver on that, right? That is to prevent bacterial growth on them. They are, fine silver nanoparticles. The other thing, we also saw that nanoparticles can change color, and in response to the properties such as temperature, pH, etc., this will be very useful for applications in diagnostics. And the other important thing is nanoparticles can fill in porous spaces. They're very, very small. You take a bulk material, you can fill it up with nanoparticles, then the material becomes very strong, and this will be useful in the biomaterials application. So the 4 properties of nano, that's what we're going to see. So one can make nanoparticles. I will not go into the methods of that. You can make metal nanoparticles, you can make polymer nanoparticles, you can make some other organic, drug nanoparticles, etc. After making the nanoparticles, what you can do is that, this gives, all the ones, gold, silica, this is liposome, the magnetic nanoparticles. You can make any of the nanoparticles, and to the surface, you can add a series of other molecules. You can make chemistry. There's a beautiful chemistry. So with that thing, you get what is called as functionalized nanoparticle. Nanoparticles otherwise are inert. If you add something, they can functionalize. For example, if you add a receptor or an interaction ligand here to a chain, this ligand can go and send something on a membrane surface or so. Then that gives rise to some signals or particles. Similarly, you can attach radioactive materials, or you can attach a DNA into that, or you can attach a targeted ligand. You can attach a drug molecules. So by attaching these things onto the nanoparticles, you change the chemical properties of nanoparticles and make the best use of its physical properties. Now, the nanoparticles, when you come to not the atoms, we already talked about the gold and silver nanoparticles, but the A, it is called liposomes. These are all small lipid chains. The detergent, the soap what you use, that has got detergents, they are called. They have got a long hydrophobic tail with a hydrophilic head group. So if you put them, they all organize them like a balloon, and inside there is space, and you can put some drug molecules into that. So you have a hydrophobic coat in which you have the drug molecules, and they will be very useful. I will tell you how they will be very useful. You can create similar structures of taking a long polymer, and you can attach some conjugates that is given in B. They again, they organize themselves in such a way that all the hydrophobic groups go inside, and you can trap something. Micelles or the detergents, the soap action comes because of micelles. Or you can make dendrimers. Dendrimers are molecules which keep on branching. It starts from there, they keep on branching like that. They are the closest mimic to what the nerves, the neurons are there, dendrimers. Or you can have carbon nanotube. I think earlier you saw a graphene. You just fold it, you get a carbon nanotube, and again you can functionalize. So these are all in the nanometer dimensions. You can functionalize them, attach some other chemical molecules, and you change the properties. In fact, gold nanoparticles also, you can attach something. So now here I introduce a kind of material called quantum dots. These are nanometer-sized crystals that contain free electrons and emit photons when subject to UV light. Earlier you saw how by changing the size of the nanoparticle, you can change the color. But here, it also depends upon the shape. And here it is shown the color emitted by a quantum dot, which is a semiconductor nanoparticle. It depends on its diameter and the shape. You can see on the other side, the different quantum dots, they give different colors. This is a cadmium selenium nanoparticle, the quantum dots. Now, why are these useful? You can take these quantum dots and they can be injected into a subject, into a cell or a animal. You can inject them. Once they go inside, then you can localize, you can detect them by light. You can exactly know where these quantum dots are going inside a cell. Are they near the membranes? Are they going to the nucleus? Or they are in the cytoplasm? I'm sure all of you are familiar with the structure of cell. So you can easily track them. So by attaching something to these quantum dots, you can get, either you can attach a drug molecule, or you can target them to a particular kind of cancer cells, etc., and you can actually detect them. This shows the imaging of quantum dots on cellular structures. You can see that in the down. Now, since we said that the size depends upon the emission, so you take a mixture of these quantum dots. Here it is going, the size dependent. You see the blue, green, and all that. You put them in a mixture into a cell. What happens on, depending upon their size, they go to the different parts of the cell. So you can see that here, you can see that it is actually lightening up. Some of the yellow ones are all localized in the membranes here. They are in the cytoplasm here. Sorry, this is in the outside extracellular matrix. So it's a multicolor image showing fixed human epithelial cells. Epithelial cells are the skin cells. So you can actually see the shape of the cell, the sizes of the cells, where these materials are going. You can do that. So you can use this for diagnostics or contrasting agents. For example, here it shows, in the A part, here you are seeing the quantum dot here. These are all binding to some cellular structures. These are 0 seconds. As the cell changes its structures, you can see that by the time you go to 180 seconds, the outside things have all changed. Either they're degraded or whatever it is. So you can see how the cell shapes change by using these quantum dots. And here you can see the lower one, the red ones, and again, the central part is missing. So when you treat cells with certain external agents, maybe drugs or some other environmental thing, how the cell changes, you can really mark them through these quantum dots. Now again, here this shows the quantum dots above is the quantum dots to which you attach a carboxylic acid, or you can attach a polyethylene glycol chain, or you attach a polymer. When you attach them and you put them into a mouse, where all they go? The brain, the heart, there is nothing going into the heart here. Kidney also nothing much is going. You go to liver, the red dots, you see that. They are going to the red dots, this quantum dot. And again, between the carboxylic acid, polyethylene glycol, and PCMA, there are some differences. The lung, spleen, tumor. So you can see, it may be because of the light, you may not be able to see that. The lower two panels show that they are getting into the tumor cells, these quantum dots. And again, the PEG and the PSMA quantum dots are better in going to the tumor cells. So you can take these rats, for example. The left-hand side is a normal one. The right-hand side is a cancerous one. So I don't know whether some light can be dimmed because some pictures will come better. Is it visible? Okay. For me, it's a reflection. I'm not able to see. Okay. So you can see on the left-hand side is a normal rat. The right side is a cancerous one. By putting these kinds of quantum dots, you can see in the last one, where you can see that here, you can see this nanoparticle, this one quantum dot going into the liver here, the one. So whereas it's not there in this normal one. So this is the cancerous one. So you can use them for imaging or detecting where the tumors are. Now this shows, the quantum dots again. Now you can also use some organic dyes. You can see color because of two things. One is due to organic structures which are called as pigments. They're all conjugated molecules. You can see color. Whereas when you come to nanoparticles and quantum dots, there are no such structures. They're all the same ones because of the color and because of the size, you see different colors. So here, if you put organic dyes, you don't see very much of contrasting thing. Whereas when you put these quantum dots, you're actually seeing. In fact, not only you're seeing they're distributed over 3 ones. I will tell you why do you see that. What you can do is that these are actually the tumor. This mouse has been specially prepared or engineered to have 3 different kinds of tumors. So by putting these different color quantum dots, you're able to see where these tumors are with these things. So the quantum dots are very, very helpful in imaging or in diagnostics. You can also use not only quantum dots, you can use what are called the single wall nanotubes. And again, this shows the single wall nanotubes, how we can use them when they go inside. The nanotubes functionalize with polymerizable lipids, You can see here it is in lungs, it is in kidneys, this is liver, and this is in spleen. In spleen, they're spreading all over the carbon nanotubes, and the lower panel shows from the side. So you can also use single-wall carbon nanotubes for imaging. And then targeting quantum dots for intracellular imaging. So this again, it shows how we can take the quantum dots here, attach some things. QD&C is a lipid-coated quantum dot, and when you put them inside, the cell outside, one of the things is very, very difficult to go inside a cell. The membrane, all of you know that the cells have membranes. They've evolved over millions of years because they don't want outside harmful things to go inside, or the important things which are inside, they cannot go out. So they have been designed like that. So when you make a drug molecule, the biggest challenge is how to take it inside the cells, because the membranes will not take them inside. So you have to use a lot of tricks to get the drugs inside the cell. So here what is done is these quantum dots, they are coated with lipid, and you put them, these ligands here, they can bind to the receptors on the cell surface. You have the cells, the membranes, a lot of protein molecules are receptors. They go and bind to them. That binding helps them go inside the cells. It's called receptor-mediated entry. So they get ingested. Once they are inside, then there's a decomposition happens, and if it has a drug molecule inside the red dots, the drug, they get released, or the quantum dots can get released. So you can use these tricks. Now here is shown a free quantum dots, and the right-hand side is a quantum dot which is coated with ligand-coated quantum dots, and you can see those red spots which are gone inside the cells. This intracellular uptake is enhanced by using these ligand ones. And the down, it shows the imaging of nucleus. You can see the nucleus through staining with a dye called hex that goes essentially to the nucleus. So you take a cell, by putting this dye, you can see where is the nucleus. By putting other quantum dots, you can see that they are outside the nucleus. They are in the cytoplasm. So it helps in diagnosis. Now here again, you can take quantum dots and add a ligand which is specific to one type of cancer. You can add another one which is specific to another type of cancer. So you can use that, and here you can see that the aggressive cancer cells and the mild cancer cells, you can distinguish them. That's what you saw on the mouse before, the 3 different colors. So you can specifically detect the cancers by finding out which is the receptor and attach quantum dots, and it helps in the early detection of cancer. Now, the other thing you can do is that also sensing, this is outside the cells. For example, cocaine and all that, these kind of drugs, if you want to generate a very, very sensitive method for detection, you can use this. So here in the blue one, what you see is, these are all gold nanoparticles to which DNA chains are attached. So now in this one, they are complementary. So because of this thing, they got 4 of these nanoparticles spaced exactly in that manner. So because of that, you get a color, because of the plasmonic things, interaction between the gold nanoparticles. When they bind to cocaine, what happens is that the structure opens up, and when the structure opens up, these particles go apart, and you see the change in the color. It is so sensitive that you can detect zeptogram, 10 raised to the power of minus 21 gram, you can actually detect by using these methods. You can also use for DNA sensing. The way in which the criminals are detected is to get the DNA and match the DNA. How do you do that? You can take this kind of nanoparticle, attach a DNA one, and here there is another nanoparticle. Because of the fluorophore, there are 2 fluorophores. And because of the 2 fluorophores, they give a signal which is called as FRET. You don't worry about that, you get a signal, because they're very close. If they're within 5 nanometers, you see a signal. When you add the target DNA, what happens is that this target DNA goes and binds to this region, it opens up. Because of that, the 2 chromophores, they go very far apart, and you lose, and you see the fluorescence only from the yellow. So by losing or gaining signal, you'll be able to detect. If this DNA is not, target DNA is not exactly complementary, you won't see that. So this is how you can use nanoparticles and their properties for diagnosis. Now here, it's called electrobiosensing. Can you sensitize this by electricity? So what you can do is, this is called glucose oxidase. It oxidizes glucose. That is was used in insulin, in sugar strips for diabetes when they use this glucose oxidase. So here what is shown is that, here we have an electrode through a disulfide bond, a nanoparticle is attached here, to which another ligand, FAD, is attached. So when you add this thing, glucose oxidase, this is a cavity which can bind to the FAD, it goes and binds. The moment it binds to the FAD, that is required for the reaction, if there is any glucose, the glucose reduces this, and the electron is transferred to this, and through that, you can detect the electrode. So this is called as electrosensing. All these things, again, because of the fine particles, Now let's come down to the very quickly to the drug release. So there are several kinds of nanoparticles, which I said earlier. You have dendrimers, you have multifunctional nanoparticles, you can make liposomes, polymers. So all these things you can use for delivery of drug molecules. How does it happen? Now, when you put a drug inside what is called liposomes, these are, it's trapped here. Due to some response, it starts opening up. It could be due to a pH, or it could be light triggered. To the environmentally triggered one, it opens up, and then these things get leaked out. So when you have this drug put inside the liposome, they go and bind to the membrane, and because these two have similar structures, it slightly opens up. Because of this, all these drug molecules go inside. So this is called as the drug delivery. This is one way of delivering a drug which is insoluble. Yeah. So let me very quickly show only one example of what happens in cancer cells. Now, in the cancer cells, this is a blood vessel, and what you see here is a tumor. The tumor grows, it requires blood supply. So this is a passive one. So what you see here, you see this cell lining here, whereas where the tumor is binding, there is a lot more gaps. So the cancerous, the blood vessels, they have large gaps. Because of that, the drugs can easily, when you have a drug, you put the nanoparticle drug, through this hole they can go inside, selectively to the cancer cells. Whereas the normal cells, where the gap is very small, these nanoparticles don't leak out. So you can utilize this method, and you can actually deliver drugs specifically to the cancer cells. Now this shows, not only drug, you can also deliver siRNA. That is also one kind of DNA-based drug. You can do that, and here it shows a healthy tissue, and this is the sick tissue treated with non-targeted one, but when you target it, it kills only the sick cells, but not the other ones. So there is already, this is not just a fiction, there is a drug available already for Doxil, which is a ovarian cancer. It is used using liposomes. There is also Abraxane, is a Taxol-based one. It's available for treatment of breast cancers. These are made out of liposome particles. And one can also use carbon nanotubes, another kind of nanoparticles for delivering the drug. And here you can see this, carbon nanotube actually getting inside the cells, and you can detect them, where they are going, etc., and you can use them for getting. You can also combine both the detection and the diagnosis. You can put the drug and the imaging together so that you can actually watch, where, for example, here, you inject the nanoparticles, and here is a tumor, and these are directed, so they go and bind specifically to the tumor, and they destroy the tumor, and they kill the cancer cells. So this is called as theranostics, therapy plus diagnostics put together. One example from Alzheimer, not only for cancer, in Alzheimer you have these peptides, they all aggregate, and by using these gold nanoparticles and you show microwave, it generates heat locally, and these things, they disappear, and that's how the one drug for Alzheimer could be done. So one example in that I'll show you in the tissue engineering, the third one, bioplants, I was telling you. In tissue engineering, what happens here to grow different kinds of cells, and it's not very easy to grow them. They require a scaffold. So you can make a nano scaffold here, biodegradable polymer nano scaffold, put the cells, and then they go exactly the shape, like skin or heart muscle, etc., and then you can take this and implant into the body. So here, it shows how you can utilize this, organ, heart, cardiomyocytes, or liver cells, or a bone, and then you can specifically implant them, again, using these nano scaffolds. This is about how to repair hearts using these tissue fibers, and you can also grow nerve cells, neuron cells, and put into the place where it is required. So now you can also combine with what is called the 3D printing, and actually you can create the nano material, bioprinting of blood vessels or metal implants, etc. You can do that. So I will skip in view of that thing. And what I want to tell you is that there is a great progress happening. This shows about the potential. Alzheimer, there is a low potential of getting a drug, but if you see on the other side, there is a major potential for cancer, cardiovascular diseases, metabolic, viral infection. So nanotechnology is coming in a big way. So finally, just 2 slides. anything, we are talking all the positive things about nanotechnology, but nanoparticles are like Janus. Janus, the Greek goddess with two faces. So there is a good face and also a bad face. There is a lot of toxicity can happen. If you start injecting them, and we still do not know what kind of toxicity problems can come. There are also size-dependent toxicity, material-dependent toxicity. So this is greatly required because you may get cured of the disease, but you may die of toxicity. So one has to be very careful. There are several mechanisms by which this toxicity they come. So the benefit from the advances in nanotechnology in medicine is that you can use for diagnostics, you can use for delivery of the drugs, you can do implantable devices, therapy, and tissue engineering. So it gives you the improved quality of life. So this is about the advantages, the benefits of nanoparticles for human care. Thank you.
Fascinating, very nice. Very.
Yeah.
Thank you, Professor Ganesh, for this very fascinating exposition of nanotechnology in health sciences. Now I see that we are already at 1 o'clock. I'm sure you are not hungry, right? You are hungry for more of science or more of food? Food. Okay, then we close it. All right, so I think what we have probably, if you don't mind, we can take some question answers for 10 minutes, if you are all willing. Are you willing? And then we can disperse. So, because I do want to give you a chance to see if you have any doubts or questions or comments, and our experts can answer. So, are there volunteers who can take the questions?
They can talk.
Okay, I think since we don't have that much time, let me just ask, you can raise your hands if you want to ask question, identify yourself instead of collecting the sheets because that may take time. So let's go to the other mode, direct interaction. Any question?
One can come this way.
No? Yes, at the back. Can some mic go to him?
There are two mics, one can be passed.
Okay. Switch off these lights, please. I can't see anything. No, this light can be seen. Yeah, floodlights can be off. Thank you. Yeah, yes, please.
Yeah, good afternoon, sir. So this is Vanshika Jindal from Schneider Electric. Sir, as we have seen in Delhi, there is so much air pollution. So I just wanted to know how nanotechnology can be used to control the pollution and convert toxic gases into non-toxic gases.
Ashok.
Okay, so there are a lot of groups which are working on filters. Okay, so you can make filters. Like, your car also uses filters. So there are mostly departments which work on fibers, like polymers or textile, these kind of departments in IITs and elsewhere. And CSR labs.
Close to you?
And some CSR labs where they are making these kind of filters where you can wear them. And actually one product has come from IIT Delhi which they are trying to market by some BTech students. They have started a company where the filter you can't even see because the filter is not that big. The filter is like kind of, like you have a Band-Aid, that kind you put it on your nostril. So, and it's brown in color, light brown. But there are, I think, still some issues about it. But they demonstrated the product and they went to government also to, like Government of India under Ministry of Science and Technology has a department called TIFAC. The technology, forecasting and all that. They give support.
Thank you. Yeah, we'll keep questions short, answer short.
Okay.
So that we'll have nano questions, nano answers. Yes.
Good afternoon.
Yes, there was a question there. Yes. can you please?
Hello? Hello?
Yes. Oh. Yes, can you?
Good afternoon, sir. My name is Kumar Dubey. I am a student of MSc Biotechnology from Reva University, Bangalore. So I have a question on, can the quantum dots be used to detect the tumors present in the body? And if yes, how in the surgery process, can the nanoparticles, nanotechnology can be used to perform the surgery? As for now, we have many major techniques. So
Okay, thank you. Yes.
Yeah,
Professor
this
Ganesh.
first question is already showed how quantum dots can be used to detect tumors, right? You can functionalize them, put a receptor. I showed some pictures of the mouse, etc. That is possible. The second one, doing that requires nanorobotics, you know. It requires robotics to perform surgery. And already I think some robotics are available. And very recently I heard some kidney transplant was done entirely through a robotic one.
Yeah. Any other? Yes, on this side. Yeah, please.
I'm Surya from Christ University, and I have a
After
doubt.
this.
As nanotechnology is progressing, we are reaching to a level where capacitors and transistors are reaching the quantum realm. So aren't there many effects such as quantum tunneling and entanglement which will cause problems when we enter such a small arena, so in such a small stage? Or are there any ways we can use these properties in order to enhance electronics which are already existing?
Yeah.
Okay, you are right. You can't go beyond a certain limit, then the quantum effects start coming in. And one of the things is that use those quantum effects to get better devices, right? For example, this tunnel magnetoresistance, those kind of things are really making use of this tunneling. And also the vertical integration. See, once you have a limitation for the lateral shrinking, but the third dimension is free for you, and people started thinking about how to get into the third dimension without affecting the physics.
Actually, it's a very, in addition, you have heard of capacitance in high school, right? So it is epsilon A over D, but that is called geometrical capacitance. When you have nano devices, as you said, it will also depend how many electrons you have put on each plate. And that is called quantum capacitance, which depends on how many electrons are put and so on. So what you're saying is right. There are these quantum effects which will be very, very important, and as Professor Anil Kumar said, are in fact used to make new devices. So that's the whole point. Thank you. Any other? Yes, sorry, before that, extreme right. Yes, pink.
Good afternoon, sir. I'm Musfira Khan from Mount Carmel College, and I want to know what are the qualifications required to get into nanotechnology. Do you prefer engineers or do you prefer science graduates?
Okay, since now I will take what you need for nanotechnology is really you have to be good in your own subject. So as I think is very obvious from all the examples presented, it is truly an interdisciplinary subject. So you have to know good physics, good chemistry, good biology, good material science, good engineering. So that's what you need to do. So when you say I am studying nanotechnology, it means you are studying all these subjects. So that's what prepares you to do nanotechnology.
Thank you.
Thank you. Something here, right? Yeah.
Good afternoon, sir. Myself, I'm Varsha from Reva University. So there was a slide like in the second presentation that the nano-sized molecules are related to the surface tension of the legs of insect and water particles on the lotus. So how is that nano-sized particles are related to the surface tension?
Nano-sized particles are related to surface tension. No, what I think, the lotus leaf, let me take the example. So if you look at the surface, with your eyes, you will not see what is there. But if you look under the microscope, then you will see features, okay? Now these features change the kind of interaction water will have with the surface. This is a property called surface tension, which you study in physical chemistry or in chemical engineering. So this surface tension is like a force, okay? It is measured in newtons, piconewtons, like that. Some newtons you will get. And it will, depending on the force, the water droplet shape will change. And you can calculate what is called the contact angle. And there are instruments by which you can measure the contact angle. So surface energy, surface tension, contact angle, they're all related to the surface structure. And in nanostructures, this hydrophobic property will be enhanced. And that's why it is called super hydrophobicity.
Thank you. Yes.
Good afternoon, teachers and delegates. I have a question. My name is Salome. I'm from Krishna College pursuing my biotechnology. The question is, we have the magnetic nanoparticles. So does magnetic nanoparticle get influenced by temperature?
Anil?
Yeah, of course. The magnetic nanoparticle, the property of the particle itself get affected by the size. Beyond a critical size, it loses its magnetic property sometimes, and the temperature also changes its magnetic property.
Then how can we bring it back to the normal state again?
Pardon?
If the temperature influences the particle, how do we bring it
So we work with the particles whose size is such a way that at a room temperature where you want to work, the properties are persisting. So you won't go beyond a certain limit. And if you still want to have a property, there are some other fundamental property like anisotropy and all will be controlled so that you get the property at the room temperature or the temperature at which you are interested in. So the application is at different temperatures. So you tune the particle, not only the size, even the other property. You know, you have the periodic table available with large number of elements. You tune them so that these properties are present at the temperature where you want to work with.
Thank you.
Yes.
Good afternoon, sir. This side.
Oh, yes.
Yeah. Sir, I'm a student of Department of Biotechnology from Oxford College of Science. My question is that can we use these nanoparticles for diagnosing any genetic disorders in prenatal stages?
Ganesh.
You say the temperature?
No, no.
No, prenatal stages. Like,
Oh, genetic disorders.
yes, sir.
Yeah, one can use, for the, genetic disorders, at the genetic level means it is due to different DNA sequences, right? You have a normal one, it becomes mutated, it becomes, genetic aberration.
Yes.
So you can utilize, and I showed one slide in which there were 2 nanoparticles, to which DNA was attached. So you can use those nanoparticles, extract the DNA from the patient, and check for that particular sequence, but through sequence matching. It's possible to detect genetic diseases using DNA anchored to a nanoparticle. Nanoparticle only helps in the detection part, whereas the actual matching happens because of the DNA sequence.
Sir, we can do that at prenatal stages. My question is that, like when the child is inside the
Prenatal
mother's
diagnosis.
womb only. That
Oh, placenta you can take it from the placenta.
Yes.
Okay.
Yes.
Yeah.
Okay, so what I think we'll take last 3 questions.
Thank you, sir.
And then we will close this session. Yeah,
Hello, sir.
yes, yes, please.
The one with the cap? Okay.
Yes,
I am professor and dean from the Agriculture University. From this year, we have introduced exclusively one course on elementary nanotechnology as applicable to agriculture and other allied subjects. Such a move is there in VTU, like engineering subjects, exclusively one subject applicable to all disciplines, and so also for MBBS course, medical course.
yes.
At the university level.
Very
Rajendra
good.
University
Thank
or
you.
VTU.
Thank you. Thank you
Hello,
for
sir.
informing.
Hello, sir. I'm
Yes,
Ranjana from
second
Bangalore.
one, yeah. Yeah.
Hello, sir. I am Ranjana from Bangalore University. Can we able to cure cancer cell at final stage by using nanoparticles at final stage?
No, there's nothing like cure. Cancer, you have to just keep it at without getting it worsened. So if it is an advanced stage, one can only do it up to some point. You cannot completely cure.
It should not be regenerate.
Yeah, regeneration is difficult because cancer, what happens, there's something called stem cells. Still, there is no technology by which you can target the stem cells and kill them. So you may kill all the secondary ones, but the parent stem cells, even if there is one, it will start multiplying. So once it goes to the advanced stage, it may be very, very difficult. You can only prolong, you can decrease the production of new cancer cells, but it's almost impossible to cure as of today's technology.
Okay, we'll go to the last question
Mike?
of the, no, there are 2. Okay, last but one. this and then you the last. You have the mic already? Yes, you have a priority. Please.
Sir.
Good afternoon, everyone. I'm Shalmali Chatterjee from Garden City University. My question is, what is the mechanism behind such antimicrobial properties of shark skin?
Antimicrobial properties of shark skin.
Yeah. The antimicrobial property
Can you put close to your...
is due to the structure. It is because the bacteria and fungi cannot stay there because of the structure. Shark is moving in water. So there's a water flow opposite. Because of the nanostructures, nothing can sit there. That is the point. There's no, it's not killing the cells. It cannot stay and grow. So bacterial layer cannot stay. Because of the nanostructures and the movement of water, the fluid flow, because of the structures, does not allow the bacteria.
Okay, thank you. Okay, yeah, yes.
I'm Suman from Government Science College. I'm studying MSc Biotechnology. My question is on cancer, sir. There are two major groups of cancer. One is benign tumor and other is malignant tumor. Sir, you said that when we give nano drugs on specifically, it will go and kill the cancer cells. But it is I think it is applicable to only to benign cancer because it will grow only on your specific sites. But
can you put your question in a nano form? What is the correct question? Because we are running out of time and we have to be very sharp.
Sir, but my question is that when we go through on that malignant tumor, it will spread throughout every tissues. It will invade in other tissues also. In this area, we can able to apply this nano drugs because it's invading and infecting other tissues and spreading on. We can do it, sir. That's my question.
Yes.
You said we can do it.
Yes.
Is it a question? Can
so
we do it
question is, can you do it? Can you do it?
Oh, no. See, you have to target this quantum dots or whatever the drug to specific cells. So the benign and the malign ones, they have different receptors. So if you actually target them, you can certainly deliver. The simplest principle is delivering to the malign or benign based on the receptor.
So at the risk of being very unpopular, I have to close this session. And we are so glad that you have still more questions left. I'm sure you will have opportunity, catch them when we come down. And thank you very much. So we'll meet next year, and I'm sure you will have opportunity to interact with many more experts as we go along. Thank you very much.
I request all of you to kindly stay back for just a couple of more seconds. We will honor the speakers. They have spent their time and energy here talking to you all. So I request Dr. Honegowda to kindly come up onto the stage. Dr. Honegowda, Special Director, DST and Managing Director, K-STEPS, Government of Karnataka. So I request you to kindly present tokens of our gratitude to the speakers. To Professor Ajay K. Sood, who has chaired this fantastic, very interactive session. Professor Krishna N. Ganesh, Professor and Director, Indian Institute of Science Education and Research, Tirupati. Thank you very much, sir, for being here and sharing your thoughts with our young audience. Professor P.S. Anil Kumar, Professor, Department of Physics, Indian Institute of Science, Bengaluru. Professor Ashok K. Ganguli, Director, Institute of Nanoscience and Technology, Punjab. So the highlight of this 9th edition of nanotechnology was engagement with the younger generation, with the student community. And this session is certainly, this session certainly suggests how far this event has gone and how this engagement with the younger audience has been. So this is a great opportunity for you all to keep yourselves abreast of what is happening in this industry and the academia.